That question to do with stellar evolution, cosmology, and also in this particular video we're going to that question to do with stellar evolution, cosmology, and also we shall look at HR diagrams so that you can be able to prepare for your exam. So here I've displayed a representation of HR diagram. So what you need to understand, you have different regions. You need to know different regions that represent a HR diagram. We have actually 4 main regions. We have a region where we have the white dwarfs, and this type of stars are almost towards the end of evolution of a star. Then we have also this main sequence where most of the stars are, and currently the sun is in the main sequence stage. We have this one where which we call the red giants, and finally we have the red super giants. So different stars evolve in such a way that they can move from the main sequence to the red giants, and then they move to the white dwarfs, which later cools down to become black dwarfs. But there are other stars, which are those stars which have mass greater than that of the sun. They move from the main sequence to the red supergiants, then which now move later to the supernova. And a supernova is an exploding star, then which becomes either becomes a neutron star or a black hole. Right, so we need to identify that white dwarfs are very hot, but they are less bright because their luminosity is less. So white dwarfs, these are hot stars, but they are less bright, and they are less bright because they are small in size. Then when we move to the main sequence, these are stable stars in the sense that the inward force of gravity is equal to the outward force due to the forces, that is expansive forces that is from within the star. So a star that is in the main sequence is actually stable. Then we need to look at also the red giants. The red giants are cool and bright. At the same time, red supergiant are cool stars but bright. Remember, they are big in size, so they lose a lot of heat, and then they are cool, but due to their big size they look bright. That's why you can see they are on the top part of the HR diagram. I think we need now to also remember that on the x-axis here we have color, and on the y-axis we have what we call the luminosity. So let us now talk about cosmology. Remember, cosmology is a topic that deals with how the universe originated. Where did the universe, it talks about the origin of the universe. And according to the specification, we are going to base our discussion on Big Bang theory. So if you are asked a question to state and explain 2 evidences that support Big Bang theory, you need to remember that the first evidence is the presence of cosmic microwave background radiations, which are everywhere and spreading or stretching in all directions. They are stretching in all directions and they are everywhere. And they might have been created during Big Bang, and that is why it serves as an evidence. The second evidence is the redshift that is observed of light observed from distant galaxies. Many galaxies display redshift, which is an indication that all this the universe is actually, which is an indication that the universe is expanding. So this is an assertion. That is what Big Bang theory claims. So we are going to say that the redshift indicates that the universe is still expanding. So that those 2 points serves as the evidence for Big Bang theory. Another part that you need ideally to prepare on is Doppler equation, the use of Doppler equation, how to do the calculation, and that will enable you to work out the speed at which a galaxy is moving away from the Earth. Now I want you to look at the scenario whereby we are told that a source of light in a laboratory is found to have a spectral line of wavelength 438. So don't be so much worried about this spectral line or what. The main idea there is the wavelength that you are told, and that is going now to be our reference wavelength because we are looking at it from the lab in the on Earth. Then now the same line from a distant galaxy, that is the same light that is emitted from a distant star, is found to have a wavelength of 6 or 8 nanometers. That is nm. Nanometer means that's 10 raised to power negative 9. So we are supposed to calculate the speed at which the star is traveling away from Earth. Now we are going to be given also the speed of light, which is actually 3 times 10 raised to power 8 meter per second. So the first thing we need to do here is to write the Doppler equation, change in wavelength over the reference wavelength, equals to the speed of a galaxy or a star over the speed of light. Then we can now work out the change in wavelength by subtracting the two wavelengths, and we're going to get 170 nanometer, which we are going now again to substitute into the formula. And remember that this is going to be our reference wavelength, lambda naught, and then 438, yes, v is the speed of the star, and now times over 3 times 10 raised to power 8, which is the speed of light. We make v the subject of the formula so that we can be able to work out the speed at which the star is moving away from the Earth. So let us try to work it out. We are going to get our answer is 1 point. Let us use our calculator and try to see 1.16 times 10 raised to power 8 meter per second, which can be equally be written as 1.16 times 10 raised to power 5 kilometer per second. I've just divided that answer by 1000 so that I can be able to get in kilometer per second. So that is the speed at which the star is moving away from the Earth, and that is how to use the Doppler equation. Moving down, we have further questions on HR diagrams. I believe you can also be asked a question in this manner. The figure below shows an incomplete HR diagram with different regions not really well labeled, but we have the middle one, which is quite diagonal, and that is very easy to identify. That is the main sequence, whereby we have the Sun. Then we have the region A and also the region B. So we need to identify what A represents. A, actually, if you look at it from the previous section that we looked at, that is the white dwarf, where we have the white dwarf at that particular point. And we said these are hot stars, but they are less bright because they are small. And then down here, on the top, we have red giants. And now I want you to write in the comment section, what is X? What does X represent? Yes, just write that so that I can see whether we are together. There's this particular part also. We're supposed to label the missing part of the HR diagram axis. So this one is color. If you are given a question and you are told to identify, is color. I remember blue stars are hot, but red and yellow stars are cool stars. So you need to remember that. The next question here, you are supposed to describe the stages of evolution of a star with mass similar to the Sun. When you are told to describe different stages of evolution of stars, remember to check whether is it similar to the Sun or is it mass greater than that of the Sun. Now in this one, part C is similar to the Sun. So the first thing you need to remember is that when you are describing this stage, you must give details. You must give details, and also you must be chronological in a given nice and good order. So you start from protostar, you move to the main sequence, you move to the red giants, then you move later to the white dwarf, then which cools down to become a black dwarf. So let me just briefly mention something to do with this. When you are writing this, already have done this question in the previous video. If you have not watched, check. I've written all the stages as the way they should be written in an exam. Now, gas and dust particles called the nebulae are pulled together due to gravity. And as they are being pulled together, temperature and pressure increases, and this results to the fusion of hydrogen and hydrogen nuclei. And in that way, heat is generated from within the star and it becomes a protostar. That star now, when it's at the protostar stage, the reactions increases, enormous amount of heat increases, so there is an outward force that is generated. Now when the outward force equals to the force of gravity, the star now enters a stage which is known as the main sequence stage. In the main sequence stage, there fusion of hydrogen and hydrogen nuclei continues, which result to the formation of helium. So when hydrogen is used up, the star is going to run out of fuel, and then it's going, now the outward forces will be less, then the star will collapse against or due to its gravity. So the size again shrinks, becomes small due to the compressive force. Temperature and pressure increases. Then that star again, new reactions come up, which are fusion of helium and helium nuclei. Now a star again becomes alive, so that this reaction of helium and helium nuclei result to enormous amount of heat and temperature, which makes this star again to expand and become a red giant, which cools down because of the large surface area. From the red giant, the star now, the reaction of helium and helium continues until the helium nuclei are used up. Then that star again now is going, because it will run out of helium nuclei, it will cool down and become a white dwarf. The white dwarf will cool further to become a black dwarf. Now, those are the steps that you need to describe there. Now, let us move down to another section whereby we are told the Hirschsprung-Russell diagram is a diagram used by astronomers to illustrate the properties of stars. Label the axes and use them to sketch Hirschsprung-Russell diagram, and your diagram should include main sequence, red giants, super giants, and the white dwarfs. So this is just a walk in the park. I believe we can be able to do that. Here is color, and at the top here we have luminosity. And luminosity is actually tells about the amount of heat that is given out from the surface of a star. We say those at the top are bright, those that have low luminosity, they are dim. And color, those that are blue towards where the axes are meeting, blue is towards that region where we have the axes meeting, and on the far end, on the right side of color, we are going to have cool stars. And now here we're going to have the main sequence. Here we have the white dwarf, and these are the white dwarf main sequence, the main sequence. And then which are these? What do you think? Okay, that is the red giants or giants, and further here on top of the giants or red giants we have super red giants, which are very bright. Okay, now already we have answered the Roman 2, where we have the white dwarf. And if you are told actually to indicate where we have the sun is in the main sequence stage. Now, the next question here, describe stages of evolution of a star with mass. Oh, I want the question now to be more than mass, more than that of the sun. This question should be, you need to take that into consideration. I think I need to make a change at that point. Yeah, mass more than that of the sun. Okay, so when that is happening, for a star whose mass is more than that of the sun, it starts from the protostar, it moves to the main sequence, it moves to the red supergiant, it moves to the supernova, which is an exploding star, it moves to the neutron star, and then finally it can become a black hole. So that is the stages for a star whose mass is more than that of the sun. These are evolution stages of stars which are massive. So which means at the protostar, where this is the stage, this is a young star after the nebula and dust particles have been pulled together by gravity. Then when the outward forces increases and balance with the force of gravity, the star will move to the main sequence stage. And at the main sequence stage, the star will continue fusing hydrogen and hydrogen until all the hydrogen nuclei are used up. Once that happens, when all the hydrogen nuclei are used up, the star will run out of fuel and then it will collapse against its own gravity. Then that star again, now temperature will increase because of the compression force. Then the star again now will start fusing helium and helium nuclei, which will result to enormous production of heat. And then that star will expand to become a red supergiant. It will expand to a point that it's about to explode. When this star is about to explode, it becomes a stage which we call a supernova. Then that supernova is going to be exploded to neutron star, or is going to become a black hole. We've come to the end of this short tutorial. I believe you found value from this. Consider subscribing. Share this to your friends so that they can also benefit from the same. I wish you all the best. I know this is going to be your kind of IGCSE O-level question, and I believe you've learned something from here. Don't forget to like this video, and if there's something you've learned new from this, remember to leave a comment down below and also like this video. All the best in your exams.